Welcome to Tech presented by Kaizen, where we will explore common cleaning questions and answers. This session has been pre-recorded and will include additional FAQs related to this specific topic at the end of the presentation. We hope it is 15 minutes well spent. Let's get started. I would like to introduce Kaizen's own Zach Papiez.
Good morning, and thank you, William. And thank you to everyone tuning in to this presentation. This presentation is on two commonly used bulk extraction techniques that measure ionic contaminants, ROSE and IC, and their specific use cases. As it turns out, ROSE and IC have quite different use cases. But before we get into that, let's take a look at the background of both methods. ROSE testing, or resistivity of solvent extract, is a process monitoring technique developed in the 1960s and is still used today. The method entails a bulk extraction where a board is bathed in 25% water and 75% IPA for 10 minutes with mild agitation to extract as much process or flux residues on the board as possible. This ROSE machine then, by way of conductivity meter, gives a contamination value measured in equivalents of sodium chloride per square inch. This is important to note, as the ROSE method does not always give a concentration value that is correlated to the contents of the board, but rather how they compare to a strong electrolyte, like sodium chloride. In keeping with this idea, the technique has found its greatest use case with RMA and water-soluble fluxes, and may sometimes struggle with modern-day no-clean fluxes. IC testing is a subset of high-performance liquid chromatography, which is defined by its ability to separate and quantify components in a mixture, in this case, ion species. This method is also a bulk extraction from the entirety of a board, but notably at a much higher temperature. It then separates the ionic species by way of ion exchange columns. The data yielded from this process is a concentration value often represented in micrograms per square inch. It is highly representative of the ionic contaminants that are found on the board. Next, take a look at some of the data we have gathered using ROSE and IC. This first set of data shows ROSE values gathered from B53 test coupon boards soldered with 6 different fluxes, all of which were not cleaned. First, it must be noted that many of these boards yielded a ROSE value of 0. This might be expected from the no-clean fluxes, but it was also observed both rosin fluxes as well. Knowing that there was still flux left on these boards, it seems that the ROSE method just can't penetrate that well. It also might be noted that at the time of the study, the ROSE cleanliness standard was 10.06 micrograms of sodium chloride per square inch, and none of these boards went over that threshold, not even the water-soluble boards. A board populated with water-soluble flux that isn't cleaned properly or has any flux remaining on the board is very likely to cause problems, but the ROSE method would not have indicated a failure. This next set of data was gathered as a repeat study of the previous slide, but conducted on B24 test coupons instead. In keeping with the previous data set, the rosin and no-clean flux boards' ROSE values were also very low and had many zero readings. Interestingly, the water-soluble boards also had quite low values this time around. The flux should be highly active and easily read by the ROSE machine, but if it can't penetrate well enough under the board part, then it will struggle to properly quantify ionic contaminants. Next, let's take a look at a few studies that show ROSE and IC side by side, and test coupons created with the same process. The data shown on this slide depicts boards that have been contaminated with various concentrations of sodium chloride in DI water on bare boards. The ion chromatography data clearly picks up on the sodium chloride as well as trace amounts of MSA that could have resulted from board handling. The ROSE data also closely matches the contamination amount, but it must be noted that this is the ideal case for this method. Sodium chloride is a strong electrolyte, and the method was conducted on a bare board, so there wouldn't be any problem for the IP in water to penetrate. This next set of data is from a separate study involving test coupons soldered with a no-clean flux. Within this data set, there were 3 cleaning conditions, all at half a foot per minute: boards that were not cleaned, boards that were cleaned at 1 pass, and boards that were cleaned at 3 passes. The results of most note are the ROSE data points at both cleaning conditions. The values were consistently 0 or near 0. Contrasting this to the IC results at the same conditions showed a clear difference. The IC was able to detect trace amounts of a multitude of contaminants even after being cleaned, especially weak organic acids. It can be inferred from this that the ROSE is either blind to certain contaminants at low levels or is simply unable to penetrate. IC does not have this problem. Next, let's look into the use cases for IC and ROSE and see how they compare. It would seem natural to group these two testing methods together as they both test for ionic contamination. However, their use cases couldn't be more different. The ROSE method finds its use in process monitoring. In today's world, with today's modern fluxes, it is little more than a rubber stamp test to potentially rule out the most egregious examples of ionic contamination. Ion chromatography is best suited for failure analysis. It is able to accurately discern the specific contaminants on a board and quantify them with a high degree of tolerance or confidence. Best way to draw a clear contrast between ion chromatography and the Rose method is with a simple pros and cons list. IC is highly accurate and specifies the ion species it detects. Through the use of the C3 tool, it can also be site-specific and narrow down where on a test board is experiencing the greatest ionic contamination. The drawbacks for IC are that it is a much longer test and entirely destructive to a production board. Rose, by contrast, is a much shorter test at 10 minutes and is more commonly non-destructive. The chief drawbacks for Rose are its struggles with modern no-clean fluxes. It fails to detect ionic species in these fluxes and may even damage production boards by breaking the hydrophobic barrier designed into no-clean systems. Bottom line, it is imperative that Rose and IC are distinguished before sending out for lab testing. Rose testing will give you a very shallow idea about your ionic contamination values and may even give the false impression of cleanliness. IC is a very useful tool to help diagnose failures of an ionic nature and should be considered when ionic failures are suspected. Next, let's look at a few commonly asked questions about IC and Rose. First, what solder fluxes were in use when Rose was developed? Rose was developed when old rosin fluxes were much more widely used and it has a much easier time with RMA fluxes than with no clean resin fluxes. Next, can Rose be used on no clean solder pastes? It potentially can, but there is a worry that it could break the hydrophobic barrier and unencapsulate the most active ionic contaminants, so it should be potentially avoided. Finally, what are the standard contamination limits for IC testing? The standard limits for IC contaminants are often different lab to lab and are usually process dependent. This concludes my presentation, and I'm going to hand it back to William. Thank you.
Thanks, Zach. Thank you all for watching this Tech to Tech session. If you'd like to discuss this topic further or have any questions not answered in the session, please contact your local Kaizen regional manager or send an email to tech at kaizen.com, and we will have someone follow up with you as soon as possible. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who would benefit from these sessions? If the answer is yes, just go to tech by kaizen.com, fill out the subscription form. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.